Hi, today I'm going to go over CS50's convolutional neural network project, Traffic. Normally, I give a background of each project that I do, but we have a lot of ground to cover, so I'm going to assume that you know what a neural network is and what the various additional layers are included to make a convolutional neural network. If you don't know what these are, or if you'd like more information on the assignment objectives, please check out the links below for lecture notes and additional resources. For this particular project, I'll just say the objective is to create an experiment with convolutional neural networks and fit models to a dataset of German road signs. Although it really doesn't matter what the pictures are of. I promise, it's not interesting. Fine. Here's an example of what we're working with. Happy? I started with a similar architecture as to what we used in lecture, comprised of a convolutional layer with 24 filters, and a 3x3 kernel, a max pool layer with a 2x2 kernel, a flattening layer, a hidden layer with 120 units, 50% dropout, and an output layer with the number of labels. Let's train it and see how it fits. It's a bit anticlimactic, but here's the results of the evaluation, which is the results of passing in all the pictures that weren't used for training. It looks like I've got a loss of 0.1359, which gives us an idea of the fit of this model, or the distance of the points from the classification's predictive boundaries of the model. And the accuracy of this fit is 95.87%. 95% accuracy seems just okay. I'm not sure that that would be accurate enough for driving applications. And I have no real sense of whether the loss is good or bad yet. On top of all of this, I know that the model's fit is somewhat left up to chance. So I'm curious to see how this architecture will perform over 4 more runs. So this architecture resulted in a loss range of 0.1128 to 0.2338. My instinct says that's not great. The accuracy ranged from 90.48 to 96.19. Seems like the first run was one of the better runs. The average for this basic architecture is 0.157 for loss and 94.24% for accuracy. I think we need to do a little better for automotive computer vision. I started to tweak some of the hyperparameters, but I was really working blind. Let's try decreasing the number of filters and see what that does. Okay, that resulted in a loss of 0.2208 and an accuracy of 93.33%. Not great, but still within range of the baseline. What if we decrease the number of units in the hidden layer? Nope, that was way worse. We got a loss of 0.9233 and an accuracy of 47%. Ugh. Maybe we need to increase these hyperparameters. Let's try a larger amount of filters. Hey, we got a loss of 0.1707 and an accuracy of 93%. That is at least within range again. Let's try it one more time. Woof. Okay. 88.8% accuracy. Let's try with more nodes in the hidden layer instead. A loss of 0.358 and an accuracy of 95.48%. That's still just within range of the baseline. Clearly, the fit of my model wasn't merely a function of using more or less filters or nodes. It seems more intricate than that. I knew that we could try experimenting with different hyperparameters, but this would ultimately still be working blind, so I opted to do more research. As it turns out, there are actually commonly used and pre-established architectures that people way more experienced than me have already designed. Typically, a machine learning programmer uses these pre-established architectures, following a general framework, and then they tune their hyperparameters, such as the number of filters and layer units, for their specific application. Just this tuning process itself can be quite the task. hence why some automated tools have been developed specifically to assist with hyperparameter tuning. Uncovering this information helped me appreciate how much knowledge and research has gone into the design of these architectures. And to truly understand what each layer is doing, down to the hyperparameter, requires much more education than we've been exposed to in one lecture. As a side note, if you're a student of CS50 watching this, check out my resources link for an awesome class that I found dedicated to just CNNs. It's from Stanford, and it has pre-recorded lectures and homework assignments all for free. After my research, I decided instead of just randomly tweaking hyperparameters, I'm going to focus my project on the comparison of three main architectures. One is the basic architecture taught in class, which is just a convolutional layer, a pooling layer, and then a neural network. The second one is called a LeNet 5-like architecture, which was one of the first CNNs to be used for optical character recognition. This has two iterations of convolution and pooling before the neural network. And lastly, I'm going to look at a VGG-like architecture. This architecture is a little newer than LeNet and is comprised of two repetitions of two convolutions and a pooling layer before the neural network. But before I share the results of these two models, I wanted to share something that I found really weird. In my research on the architectures, I learned that programmers make this table of activation map sizes and shapes that can help tune the hyperparameters of each layer. I definitely will need to learn more about this, but what I gathered at a high level is that you want to make sure you don't end up with a negative activation size, meaning you've somehow trimmed out too much information, and two, you want to make sure that you're not jumping drastically in size of your activation map. Here's a spreadsheet and what I think the activation map looks like for the basic architecture. Don't worry too much about the different columns. However, if you really want to know more, I'll post a link to the Stanford CNN class notes in the description of this video. Let's focus on the activation size. By multiplying our input image shape, 30 by 30 by 3, we get an input size of 2700. After the first convolutional layer, we jump up over 18,000. And then after max pooling, we only decrease our map size by a little over 1,000. I was shocked by this because when we learned about pooling in class, I thought it was like taking 4 pixels, picking the maximum pixel, and then throwing out the rest. But that's not really what's happening. No, instead, it's really like, well, listing the maximums within every 2x2 region. You end up with a slightly smaller size, but you're really not throwing out data. This is when I learned about a hyperparameter we didn't cover in class, stride. Stride does what I thought pooling did. Stride dictates how much we move over the input map. By default, it's 1. So for example, 1 pixel. But I noticed in pooling operations, the stride is often defined as 2, meaning we look at 4 map slots with a pool size of 2x2, and we pick the highest value, and then ignore the rest. This was a huge aha moment for me. With a default stride of 1, our activation size expands from 3K to 18K and then compresses to 100. That doesn't seem to follow our general rule of thumb to not drastically change the activation size. So I figured I'd give a stride of 2 a try on our basic architecture. Here we go, let's see the results. Wow, that is way worse. Not even close to being in range. Let me try a few more times. Nope. The averages for loss and accuracy were way outside of the baseline ranges for this basic architecture. So that wasn't what I was expecting, but given the analysis of the spreadsheet of activation maps, I wonder if this pooling layer is even contributing much. What if I remove it? Okay, that's incredible. With a loss of 0.1569 and an accuracy of 94.6, that's basically spot on with the baseline basic architecture averages. I guess this layer wasn't doing much. Briefly, here's a glimpse of the activation map sizes for the LeNet and VGG architectures. You'll see that while using strides of 2 in each pooling layer, the activation size for the LeNet architecture very gracefully expands and contracts, even using 2 hidden layers in the neural network to gently compress the number of nodes. The VGG architecture explodes very quickly in the first convolution and seems to decrease by an order of magnitude every 2 to 3 layers. I wasn't sure how this would work, but we will see shortly. Okay, so we played around with the basic architecture a lot, but now it's time to check out the LeNet-5 architecture. Remember, this is a convolutional layer, a pooling layer, and then another convolutional layer and a pooling layer, then the neural network. Okay, a loss of 0.1444 and an accuracy of 96.03. Not bad. Let's get 5 fits to form a baseline. Whoa, what the heck? It looks like we got an overfit. What the? Oh my gosh, a loss of 1.1431? Oh man, I'm almost proud of how terrible that is. Well, I'm just going to toss this as an outlier and run it one more time. Okay, so the ranges and averages for the LeNet architecture was honestly only a little better than the basic architecture, even without the overfitting outlier. I'm sort of surprised. I tried a few tweaks that I read are general good practices, like switching the second convolutional layer to a filter size of 3x3, or using average pooling in the second pooling layer rather than max, but these 2 tweaks yielded results that were only subtly better at best. Let's try the VGG architecture instead. Whoa, okay, whoa. So, yes, a loss of 0.0718 and an accuracy of 98.1% is delicious. But did you notice how fast that ran? Let me do it again. Wow. And this has an even smaller loss than last time. So what I haven't shown you yet is that I actually created this separate tool for this project. I created a custom callback class that could be declared when fitting your model. It generates a plot of the fit time for each epoch and gives an idea of how quickly a model can be generated. The basic architecture and the LeNet architecture had an average time around 17 seconds. This VGG architecture has an average fit time of 7 seconds. So not only does it have an incredibly low loss of 0.0584 and a high accuracy of 98.56%, it's lightning fast in comparison to the other architectures. I'd be proud to use any resulting models from this architecture in self-driving cars. Well, that was a lot to cover. I'm still left with more questions than when I started. I'd love to learn more about the various activation functions and how to intelligently tune some of the hyperparameters, and how new architectures are developed. I didn't even touch the various optimizers when compiling models or any real data augmentation before feeding the data into the model. But I guess this assignment has shown me there are vast grounds to cover with CNNs, if you so wish. They're probably not something you'll fully appreciate in one lecture, even if it is a course from Harvard's CS50. Thank you for watching.